All right, welcome. Today, we're going to build something truly fundamental. We're going to construct, from the ground up, one of the most powerful structures in all of mathematics, the vector space. Now, this is a concept that gives us a kind of universal blueprint for all sorts of things that, on the surface, seem completely unrelated. So let's just dive right in.
At first glance, this feels like a trick question, right? An arrow points somewhere, a matrix is just a grid of numbers, a digital signal is, well, a sequence of values over time. What on earth could possibly unite them? The answer, as we're about to see, isn't about what they are, but what we can do with them. It turns out they all play by the exact same set of rules.
So here's our game plan. We're going to start with the most basic idea. What are the rules of the game? From there, we'll build out the full vector space blueprint. Then we'll look at some really surprising examples of things that actually qualify as vectors. And finally, we'll see just how easily this whole structure can fall apart if you break even one tiny rule.
Okay, let's start at the absolute foundation. Before we can build this grand structure, we really need to understand the bricks and mortar. And in math, that all begins with a really simple idea, an operation. Just think of it like defining the legal moves in a game. What are you actually allowed to do with the pieces you have?
A binary operation is, at its heart, just a rule. You take two things from your collection, your set, let's call it A, you apply the rule to them, and the result has to land back inside that same set A. Now, this might sound super obvious, but it's probably the single most important property there is. It's called closure. If you add two whole numbers, you get another whole number. You don't suddenly end up with a fraction or something else entirely. You stay in your universe.
And right here, this is the formal mathy way of writing it down. That little star symbol, it just means your operation. It could be addition or multiplication or maybe something much weirder. The key, though, is that it takes two things from your set S and it guarantees that the answer lands back in S. This property of being self-contained is what makes it possible to build reliable, predictable systems in math.
So we have a rule like addition. Great, but what makes addition so useful? It's not just the operation itself, it's the properties that it has. We all know that 3 plus 5 is the same as 5 plus 3. We know that adding 0 doesn't really do anything. These are the rules for the rule, and there would give the whole system its power and predictability.
Now, when we take an operation like addition and we enforce these 5 specific properties, we get this beautifully predictable system called an abelian group. Just think about adding numbers. Closure means you always get a number back. Commutativity? Well, 2 plus 3 is the same as 3 plus 2. The identity is just 0. It's the number that does nothing. The inverse means for any number like 5, there's a negative 5 to get you right back to 0. And associativity just means you can add a long list of numbers in any order you want. This complete, reliable package is the first major piece of our blueprint.
Okay, now we can finally build on that foundation. An abelian group handles addition perfectly. But to really work with vectors, we need a second ability. We need to be able to scale them, to stretch them, or to shrink them. And that requires a whole second operation, scalar multiplication.
And here it is, the complete 10-point blueprint. Now, don't try to memorize all of them at once, just look at the structure. The first 5 rules, they just say, hey, your vector addition has to be a well-behaved abelian group. The next 2 rules handle the scaling part. Multiplying by a number can't kick you out of the set, and multiplying by the number 1 has to leave the vector totally unchanged. And then finally, these last 3 rules are like the critical glue that makes sure addition and scaling actually work well together. This is how we know that, for example, 2 times vector A plus vector B is the same as 2A plus 2B.
If you take one thing away from this, let it be this. A vector space is not just a collection of objects. It's a package deal. It's the set of objects plus the 2 operations defined on them. The objects themselves can be anything, arrows, numbers, whatever, as long as they, together with their defined operations, satisfy all 10 of those rules, those axioms.
Let's make this really concrete. On the left side, we've got the set of all 2D points, r squared, with the normal, everyday definitions of addition and scalar multiplication. This passes all 10 tests with flying colors. It's a vector space. But now look to the right. The set of objects is exactly the same. The addition rule is exactly the same. All we did was tweak the rule for scalar multiplication just a little bit. Now it always forces the second component to become 0. And that tiny change, it breaks the entire structure.
So let's zoom in on exactly why that rule on the right fails. It comes down to axiom 10, the scalar identity. The rule says that multiplying a vector u by the number 1 should just give you u right back, unchanged. But with our weird new operation, 1 times xy becomes 1 times x comma 0, which is x comma 0.
Well, that is not the original vector xy unless, of course, y was already 0 to begin with. And because this one axiom fails for even a single vector, the whole set, under these rules, is not a vector space. It's that strict.
Okay, so if being a vector is really all about following a set of 10 rules, that opens up a really fascinating possibility, doesn't it? Maybe things that we don't normally think of as vectors can actually be treated like them, as long as they just obey the blueprint.
And it turns out they absolutely can. Take the set of all 2x2 matrices. If we define vector addition as just normal matrix addition and scalar multiplication as normal scalar multiplication, it turns out this system satisfies all 10 axioms perfectly. So what does that mean? It means from the perspective of linear algebra, a 2x2 matrix is a vector.
And it gets even more abstract. Consider the set of all real-valued functions. I mean, how can a function possibly be a vector? Well, let's check. Can we add two functions together? Yeah, of course. F plus g of x is just f of x plus g of x. Can we scale a function by a number? Sure. K times f of x is just k times f of x. And if you go through and check all 10 axioms, you'll find they all hold. So functions can be vectors too.
Now for a really practical, real-world application, look at this. An infinite sequence of numbers. This is exactly what you get when you digitize a sound wave or a signal by sampling it at discrete moments in time. You can add two signals together, point by point. You can amplify a signal by multiplying it by a scalar. And guess what? This set of all infinite sequences also forms a vector space.
And that's the crucial point. This is why we do this. By abstracting the idea of a vector into a simple set of rules, we create a universal language. All the powerful tools of linear algebra, things like basis and dimension and linear transformations, we can now apply them to solve problems in geometry, in matrix theory, in differential equations that involve functions, and in digital signal processing. It unifies these huge, seemingly separate areas of science and engineering.
So now that we've seen the incredible power of this blueprint, let's look at one more example of just how easily it can fail. In the most fundamental failure, the one that stops you before you even start, happens with that very first axiom, closure. Okay, let's look at a very specific set of objects. This is not all 2x2 matrices. It's only the ones that have this very specific form. Some number A in the top left, another number B in the bottom right, but, and this is the key, they always have a 1 in the other two spots. The set is defined by that structure. All right, so let's test the very first rule for vector addition, closure. The rule says if we take any two matrices from our special set and add them using standard matrix addition, the result must also be a matrix that belongs to our set. So, let's see what happens. And there's our result. When we add them, the top left and bottom right parts are fine. They're just some new numbers. But look at the off diagonals. 1 plus 1 gives us 2. The resulting matrix has 2's where our set's definition strictly demands 1's. The result of our operation has literally kicked us out of our own universe. And that's it. We don't even have to check the other 9 axioms. The moment closure fails, the game is over. This set, with these operations, is not a vector space. It just goes to show you how absolutely essential that first, seemingly simple rule really is. So let's just quickly recap the big ideas here. First, a vector space is a package deal. It's a set plus 2 operations. Second, that whole package has to satisfy all 10 of the axioms to qualify. Third, the real power here is abstraction. It lets us apply one powerful toolkit to many different kinds of problems. And finally, the system is strict. If even one axiom fails, the whole thing is not a vector space. And that really leaves us with a final thought to chew on. If an arrow and a matrix and a function can all be vectors, it forces us to ask a much deeper question. It's not about what they look like. It's about how they behave. What is that essential, shared vector-ness that those 10 axioms are trying to capture? Well, it's the ability to be added together and to be scaled in a consistent, reliable, and totally reversible way. That is the universal blueprint.